Hey everybody, welcome back. Mr. Smith here. What I'm going to do in this slide deck is to take you through the key skills you're going to need to tackle some of the harder problems where you see series and parallel circuits working together in combination. So what I've done is I've made a fairly simple example of this, but you're going to find that inside this example you have all of the key skills and all of the teaching that you need to get so you can analyze even the worst ones. So the way it's going to work is like so. We have a positive 12 volts here. The symbol for battery is meant to indicate that the larger plate is the positive. And so because of tradition, we read charges as coming out of the positive plate and then circulating. The big thing I want you to know is that when you diagnose a circuit, the first thing you want to do is to trace it, maybe even literally with a pencil. So you can trace from the battery to this junction right here, and then charges can either go up through the 680, through the 470 and back home, or they can go leftward up through the 820 through the 470 and back home. Those are the only options for charges. They never do anything crazy like they go up through the 680 and then back through the 820. Why? Because charges don't like resistance. They always choose the easiest pathway between where they start here at the positive plate and where they have to end up back at ground, okay? So the first thing you're going to see me do is to diagnose this circuit. Now that I realize that this is a point where there's a choice, that means that these two resistors are in parallel with each other. I'm going to file that away. The second thing I recognize is that all the charges through this guy have to go through the 470, and all the charges through this guy have to also go through the 470. So what does that mean? The 470 is in series with both of these, okay? So now that I've diagnosed that circuit, what you're going to see me do is, let's go ahead and actually just nuke the diagram because I don't like it anymore. I'm going to use my own diagram. And what I'm going to do is redraw it. And I can redraw it any way I want to. The order of things doesn't matter. I like to draw series elements first. So what I'm going to do is, you'll notice I draw these things flat. There's no reason to keep them as a circuit, especially in the beginning when you're trying to simplify them. So I've got a 470. And what I realized is that I had a 680 and an 870, I believe it was, right? 820. So 680 was up here, and then an 820 was right here. And what am I going to do with this? I'm going to redraw this because the very first thing I need to do is to always get the equivalent resistance of the circuit. So on this slide, that's what you're going to see me do. And we're going to use all the skills we just used in our last slide deck. So I've simplified that circuit, and I've drawn it now as 470 connected in series with these two that are in parallel. So what can I do? I can draw it 1 degree simpler. I can draw 470 in series with a mystery resistor. What's that mystery resistor? It's the effective resistance of these two guys. So I can get that. What's the R equivalent of those two? I'm going to write it like this. The R equivalent of those is going to be 680 to the minus 1 plus 820 to the minus 1. So what did I just write? 1 over 680 plus 1 over 820, all to the minus 1. And so what does that amount to? I get out of that 372 ohms. So what have I got? Finally, I've got the value of the mystery resistor down here. And lastly, I think I figured out REQ, right? So the R equivalent overall for the whole circuit is just going to be the sum of these two because they're in series. And so when I add 470 and 372, I get 842 ohms as the overall equivalent resistance of the circuit. The biggest thing I was after, first thing I was after, get the R equivalent of the whole circuit. Now in the next slide, what you're going to see me do is to use the diagrams that I just worked with, and maybe even a simpler one, to go figure out current for the overall circuit. And that'll be the next step. Okay, so in the slide, what you can see I've done is just to redraw our circuit with just one resistor. And here I just recopied from the last slide. So what am I going to do? I'm going to get the second thing of the three major things that we're after. I'm going to get the equivalent current through the whole circuit right now. So I know that there's 12 volts, and what I'll do is just draw in a 12 volt voltmeter, reading the potential difference between this side, which is hot, and this side, which is ground. And so it's easy enough. You can use Ohm's law and get R equivalent, work that into your formula for Ohm's law. So I equals V over R. If I put in R equivalent and the total voltage for the whole thing, I get that there's 12 volts over 842 ohms, and that the current through this whole kit and caboodle is 0.0143 of an amp. Okay, so I've got the equivalent current. That's the second major thing I want to do, and it's easy once you get the equivalent current, equivalent resistance rather. So the next thing you're going to see me do is the second major thing, and this is just to start to go backwards, but I got a little space on this slide, so I might as well get after it. I'm going to take the two resistor picture of this and recognize that because these are in series, the current that flows through the network, that's the total number of electrons, is the same through this element and this element. So this ammeter right here would read 0.0143 of an amp. And what does that let me do? I can then use Ohm's law to go and figure out the voltage drop on just this one resistor. So that's my V, and I'll just figure it out down below. What does it let me do? I know V equals IR. I know the current through that resistor. So 0.0143 of an amp goes through that resistor. I know the resistance of that resistor is 470 ohms. And when I go ahead and do the math, I get 6.72 volts are dropped on that resistor. The biggest thing I want you to realize here is that in a series circuit, I never will lose 12 volts on this first resistor. The physics won't allow all of those charges to stop having lost all their voltage and just pile up. So charges are not allowed to lose all their energy on the first resistor of a series. This guy here affects how charges experience that first resistor. That's what a series does. So there are two ways, now that I've got the voltage drop on this guy, there's two ways that I could go about getting the voltage drop on this guy. If I just repeat this exact same thing and multiply by 372, I'll get the voltage drop on this one. The other thing that I could do is, because I know this voltage drop and this voltage drop add up to 12, as I could just subtract and I could get that this is 5.28. Now I did the math. I went and actually calculated the voltage drop on the 372 ohm resistor, and I found out that it was 5.3, so it didn't exactly work out the way I thought it was going to. It didn't equal 5.28, and the reason is there's a rounding issue with the current. It doesn't matter. What I've got is I've taken a major step now. I know the voltage drops across these resistors. In fact, I've got everything there is to know about this resistor. What I'm going to do is expand back now to the first diagram you saw me do and use that. Okay, so we're just about done with this thing. What we're going to do is use the discovery that we just made. I know the voltage drop on this guy is 6.72. I don't care anymore. I know everything about him that there is to know. What I did just discover, though, was that the voltage drop on this resistor, because it's in parallel with this resistor, they're both the same. So the voltage drop on this guy is 5.28 volts, I'll call it. The voltage drop on this one is also 5.28 volts. That's because the charge that runs through the 470 has to make a choice here. It can run through this one and lose the remainder of its 12 volts, or it can run through this one and lose the remainder of its 12 volts. It can't do anything different than that. And so now that I know the voltage drops on those, what I'm able to do is actually figure out the current through each one. So I'll write it as I680. So I680 is going to be V over R, 5.28 volts, divided by 680 ohms. And I'll call this one down here I820, and that's going to be equal to 5.28 volts, just divided by his resistance, so 820 ohms. And we did the math on those things and figured out that this top one is 0.0078 of an amp, so pretty small. This one's going to be even smaller, 0.00644 of an amp. And what you see happening again, more charges will choose to go through the easier resistor. So the current in the 680 is bigger than the current in the 620. This thing is done. What I've got is the current through each element. I've got the voltage drop on each element. And what you're going to see me do is summarize all that stuff in a table. And then all you do to get power is just multiply I times V for each element. So the way I would do that, for instance, for this guy right here, is the power of the drawn by the 820 ohm resistor is going to be just the current through him. So that's 0.00644 amps times the voltage drop that that resistor experiences, which was 5.28 volts. And you'll see me do that on the table. Okay, so let's just go ahead and I'll show you how that all works, and we'll wrap it up. So as you can see, what we've done is just summarized everything in a neat table for you. We've got the voltage drops on each one of the resistors, the 470, the 680, the 820, the currents through each one. Check and see, do these currents add up to that one? They sure should. And the total power. Okay, so big step in the direction of complicated. If you master those skills, though, you're going to be good to go, and you're going to be a force to be reckoned with. So take care. Bring your questions to class. Look forward to seeing you soon. Bye-bye.